So today we're diving into this really fascinating paradox at the very heart of artificial intelligence. On one side, we've got these incredible breakthroughs that promise a future of super efficient learning. But on the other, brand new research is uncovering these subtle, really sophisticated dangers hiding in the very systems we're trying to make safe. Let's get into it. For the longest time, the motto in AI has basically been bigger is better. More data, more computing power, which means more money and more energy. But what if that's not the whole picture? A new wave of research is asking this really fundamental question. Are we building AI the hard way? All right, let's start with the promise. We've got this incredible study out of Johns Hopkins University that suggests there might be a much more elegant, more efficient way to build intelligence. And the secret? It takes its cues directly from the human brain. Right now, the way we do things is, well, it's a brute force approach. We're building these massive computer clusters, some the size of small cities, and spending months, even years, training models on just trillions of data points. I mean, it works, but it's unbelievably expensive and burns a ton of energy. And this quote from the lead author, Mick Bonner, just nails it. Think about it. The human brain learns to see with a tiny fraction of the data our AI models need. So the researchers started wondering, what if the structure of the AI network itself is just as important, or maybe even more important than all the data we're force-feeding it? And here's where it gets really wild. The team built an AI using a design called a convolutional neural network, which is kind of loosely based on the brain's visual cortex. And they found something incredible. Even before a single piece of training data was introduced, these networks already showed activity patterns that looked a lot like a human brain looking at the same images. It's like they had a built-in head start right out of the box. Now that is a potential game changer. If we can start with a better blueprint, we could slash training times, which would make developing AI way faster, cheaper, and more accessible to everybody, not just a few giant tech companies. It's a really optimistic vision for where things could go. But you knew there was a but coming, right? With every great promise in tech, there's always a potential peril. As we get better at building these powerful and efficient learning machines, we also accidentally create new, totally unforeseen vulnerabilities. And that brings us to the other side of this double-edged sword. So while one group of scientists is figuring out how to make AI easier to build, another has found a brand new way to misuse it. They're calling it the elicitation attack, and it is a seriously clever way to get around the safety features of even the most locked-down models. So what exactly is this attack? Well, you can think of it as a kind of knowledge laundering. An attacker basically uses a powerful, safeguarded AI as an unwitting tutor to teach a different, less secure, open-source model how to do all the things it's not supposed to. And the process itself is deceptively simple. First, you just ask the safe AI a whole bunch of completely harmless technical questions in a related field, like, say, organic chemistry. The safe AI gives you detailed, helpful answers, because, hey, the questions themselves aren't dangerous at all. Then you take that whole library of safe answers and you use it to retrain a different, totally unrestricted AI. And this image just illustrates the result perfectly. On the left, you've got these innocent-looking questions, like how to extract a certain oil from lavender. But that underlying knowledge of chemical processes, once you transfer it to the open-source model, can be repurposed for something really dangerous, like making mustard gas. The core scientific knowledge gets transferred, completely sidestepping the original model's safety rules. So, how well does this work? Well, in tests that were focused on making hazardous chemicals, this attack recovered nearly 40% of the capability difference between the weak starting model and a powerful, completely unrestricted one. That is a massive and, frankly, dangerous leap in capability. So here's the bottom line, and it's a crucial point. The safety measures we have right now are almost all focused on blocking direct, harmful requests. They just don't account for this kind of ecosystem-level risk, where knowledge can be pulled out and used somewhere else. It's a fundamental loophole. Okay, so this tension between incredible promise and these really subtle perils brings us to a third and absolutely critical area of AI research: the mission to actually understand what in the world these models are doing. And this is the field of explainable AI, or XAI. XAI is all about cracking open that infamous black box. For years, we've had AI that works, but even the people who built it couldn't tell you precisely why it made one decision over another. XAI wants to change all that.
by giving us the tools we need to audit, to trust, and to actually verify an AI's reasoning.
Now, there's a really important difference here. Interpretability is about understanding the model as a whole, how the algorithm works in general. Explainability is way more specific. It's about being able to point to the AI and ask, why did you make that particular decision for this specific input? It's the why behind a single result.
And why does that matter so much? This slide is the perfect example. A simple evaluation, one that just checks for keywords, gives a high score to a procedure for making a chemical. But a more sophisticated XAI-style evaluation realizes the procedure makes a totally nonsensical error. It tries to recrystallize a liquid, which you can't do. So one method sees success, while the other spots a critical, dangerous failure. Understanding the why is everything.
And to get to this level of understanding, researchers are developing this whole amazing toolkit of techniques. Some of them act like detectives, tracing a decision all the way back to the specific words in a prompt or pixels in a photo that had the most influence. Others create these heat maps over images, showing you exactly what the AI was looking at to identify something. It's this deep, fascinating field that's all about translating machine logic into human understanding.
Okay, let's pull all three of these threads together. We've got this push for more efficient AI, the discovery of new ways to misuse it, and the development of tools to finally understand it. So, how does it all connect?
This table lays it out pretty clearly. You've got the promise from the Johns Hopkins study, which means AI development could speed up like crazy. You've got the peril from the elicitation attack, showing that as models get more capable, the security risks get way more subtle and systemic. And then you have XAI, which is the essential bridge giving us the oversight we absolutely need to manage that risk and actually build trust in these systems.
So, if there's one key takeaway here, it's this. Just building more powerful AI isn't enough. We are in a parallel race to build our own ability to understand and safely manage these incredibly complex systems. And one of those races simply can't succeed without the other. And that leaves us with this one last kind of mind-bending question for the future. That Johns Hopkins research is all about making AI architecture more brain-like. As we actually succeed in that goal and make an AI that reasons in ways that are more familiar to us, will that make it easier to understand? Or will it just inherit all the beautiful, messy, and often inscrutable complexities of our own minds? That's the real challenge that's waiting for us.